Hey y'all, welcome back. I'm Mr. Boyden, and we're going to continue today with more discussion on normal distributions. This is part 2 of the previous video. Today we're going to cover 3 things. First, we're going to find values from known areas and probabilities with a little bit of review baked in. We are going to learn how to assess the normality of a data set, so like looking at a set of data and saying, are these approximately normal or not? And finally, we're going to learn about something called a probability plot. So let's get to it. We're going to start today actually with an example. And this is one that I suspect that after watching the previous lesson, you could probably do most of this question. So I want to encourage you to do so, to pause the video and work this out. So step 1, draw a sketch of the distribution. So mound shaped, sort of approximately normal distribution. So 65 inches is the average. Standard deviation of 3.5. And the height are approximately normal. I'm not actually going to put those on there. I'm going to leave those off for right now. And then we're going to do a few calculations. So use the sketch to estimate what percent of women are between 62 and 68 inches tall. And guys, I'm going to draw a new picture for each one of these. So 65 is right here. And you know what's interesting? They said use your sketch. It didn't say use the calculator. Interesting. So 68 and 62, and I'm going to draw those in. And you know what I noticed right away is that this distance, and I'll put it here in red, this distance here is a distance of 3 from either side. But we were told the standard deviation is 3.5. So I'm going to go in green and just go out here. So one standard deviation is a little bit more. The area in between the two greens is going to be 68%. This is less than that. So I'm actually going to make a guess of like 0.6, and they said what percent? So I'm going to guess 60%, and we'll test that on the calculator in just a second. What I'm going to do is I'm going to get all the setups here, and then we're going to go calculate them all in the calculator at once. So part C, use your calculator to determine what percent are between 62 and 68. We made a guess. We'll go calculate that based on this picture in just a second. And then what about these down here? 60% of women are taller than what height? Interesting. I better draw a picture for that. All right, so get my curve. And 60%, so if I went from the center of the distribution, 50% would be on the right and 50 would be on the left. So it's going to be some height in here such that this area is 0.6 and this area is 0.4. And let's draw a picture for the last one as well. And so this says 20% of women are shorter than what height? So I want the shorter side to be a 0.2 on that one and a 0.8 on the right. So one thing that I hope you see already is that part C and part B, those are exactly what we did in the previous lesson. But parts D and E are different. So what do I mean by that? For parts B and C, the input is the bounds, and the output is I'm going to call it a probability or a proportion. But D and E are different. So we actually have a proportion because it's percentages. The input is a proportion. And the output, what we're going to be looking for is x values. So kind of like bounds. Bounds are on that axis, but it's going to be an x value. And so looking at that, what I notice is that the inputs and outputs are switched. The information we have and the information we're looking for is switched. So you might remember from taking pre-calculus that when you have a function and the inputs and outputs get switched, that's known as an inverse function. And up here for this, in a minute, we're going to use normal CDF. And they named this function really well. The inverse of that they call inverse norm. So these are going to be our first inverse normal calculations. So let's switch over to the calculator and let's do those inverse normal calculations now. For part B, I'm looking at my sketch, parts B and C I should say. I'm looking at my sketch and I see that's a normal calculation, normal CDF. So let's go menu, and I'm going to go 5, 5, 2, although I missed it. Let's try again. So menu 552, and my bounds were 62 and 68, and we know the mean and standard deviation, so we need to put those in. Feel free to pause if you need to check the inputs. And remember, I had guessed, and your guess may have been a little different, but I had guessed it was going to be about 60%. Let's see how I did. Oh my gosh, okay, it's about 61%. So I was off just a little bit, but I was in the ballpark, and so that's good. This demonstrates how you can use the empirical rule if you don't have a calculator or a phone with you to make really quick approximations. Okay, let's go on to D. That's the one that says 60% of women are taller than what height? Now, what we always do on this, and we said it's an inverse norm, and so menu, if you can go to probability, and distributions, it's going to be the third one down. So this is another one that you probably want to go ahead and memorize as menu 553, or if it's different on your calculator, whatever it is, that's going to save you a lot of time and you won't have to search through menus and fatigue yourself. So let's go to that command, and they ask for three things: area, mu, and sigma. Mu is the mean, so let's type that in at 65. Sigma is the standard deviation, so let's type that in at 3.5. And notice the drawings I made, I labeled the area on both sides. So what your calculator is going to do is it's going to shade from left to right, which means that you always put in the area on the left. I will go back to the other screen and write that in a minute, but you always put the area on the left. So for the first one, they said that 60% of women are taller than what height? That was the number on the right, 0.4 was on the left, so I need to put 0.4 as the area. And so what do I get with that? I get 64. If you think about it, that makes sense because that number is lower than the mean, lower than the median, so more than half, 60%, will be above that mark. Let's also calculate part E. 20% of women are shorter than what height? In that image, and you can look at your notes to see this, we had 0.2 on the left of the distribution. So it's going to be menu 553, and we're going to type 0.2 this time. So 0.2, 65, 3.5. Let's see what we got. All right, 62. So I'm gonna round these to the nearest whole at 64 and 62. Let's return back to this screen and let's check and see if those make sense. So what we had is that we thought the area was 60%, but it was actually rounded. It was 61. For the next two, we're asked 60% of women are taller than what height? Remember, the mean was 65. And we got that this number was 64 inches. Okay, that kind of made sense. And 20% of women are shorter than 62 inches. And that's 5 feet 2, if you're wondering. So 20% of women are shorter than 5'2". Yeah, seems maybe about right. Okay, so that's our first calculation from the inverse norm. Let's try another question. This one about nicotine content in cigarettes. So again, I think this would be a really good one for you to pause the video and try on your own. So give it a shot. All right, here's what I think. So for these first ones, or for all of them actually, I'm going to draw images. That always helps me, although I'll admit it, I'm very much a visual learner. So mean of 1.8, so the first calculation is less than 1.45. Second calculation, between 1.45 and 1.65. And notice I'm drawing the 1.65 to the left of center because the center, they told us, is 1.8. And then last image, or I should say third, sorry. They said more than 2.15, so 2.15 area is to the right because it's more than. And then what is the last one? What value is needed such that 80% of the cigarettes will exceed it in their nicotine content? Now, check yours really quickly. What did you type in the calculator for that one? This is the one that is an inverse norm calculation, but I hope you didn't type 0.8 in the calculator. Remember, you always use the number on the left. So I want to add that in here real quick. For inverse norm, always type in the area on the left. Okay, and I'll highlight that so it stands out. And that really is the most common mistake people make. The thing that's nice about calculators these days is if you pick the wrong function, when it asks you for the inputs, you're not going to know what to write. And so you're going to realize, oh, well, I have no idea what that stuff means, so I probably clicked the wrong thing. But you might put in the wrong area. Okay, so we're going to switch back to the calculator now, and let's type these in and see what they are. All right, so first one is a regular norm CDF. So menu 552. Lower bound is negative infinity. They already did that for us, so thanks a lot. 1.45 for the upper, mean of 1.8, and standard deviation of 0.2. This feels like it's going to be a small number to me. And sure enough, it is. It's about 4%. Okay, let's do part B. And yeah, they say the probability. So we would answer that as 0.04 is the probability. They're not asking for a percentage. Probabilities need to range from 0 to 1, right? So let's do B. So this one, it's saying that we're ranging from 1.45 to 1.65. 1.45, 1.65. And let's see what we get for that. And guys, I'm going pretty quickly because I think you've probably already done this in your calculator. We're just checking your answers right now. So I get 0.187 on that one, which makes sense. That felt like a bigger shaded area to me. Let's do part C. So menu 552. In this one, our lower is going to be 2.15. And remember, for upper, you just type a whole mess of 9s if it goes to infinity. And then 1.8 and 0.2. And this is probably going to be a smaller number as well. Yeah, again, 4%. Okay, or 0.04. And then the last one is different because we knew the area, we knew the probability, but we needed to know the amount of nicotine. So for this one, that's an inverse norm, menu 553. And the area, remember to type the area on the left as 0.2, and remember to put in the mean and the standard deviation. And let's see how many milligrams of nicotine that would be. 1.63. Let's go back and review that, see if that makes sense. So the claim is then that this value right here is 1.63. That kind of makes sense. If that's 1.8, at least this value is smaller. If you had typed in 0.8, for example, for the area, you would get an X value much bigger than 1.8. And when you draw that on the picture, you'd realize, ooh, yeah, I guess that doesn't make any sense at all. These numbers are out of order. That's another reason why it can be very useful to draw a picture. It will help you catch yourself if you make a mistake oftentimes. You'll go, oh, that picture makes no sense. I better see if I did something wrong there. The next thing we're going to do is we're going to look at a data set and assess normality. And what this is so far, what we've seen is we get questions like, well, the data are approximately normally distributed and blah, 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 blah. Well, what does that really mean to be approximately normally distributed? Where does that come from, and how do we tell if the data are approximately normally distributed? That's what we're going to do now. So what I have here is 60 data points, and it's just a data set out of the book. And we're going to use this as our first example to assess normality. So if you want to do this along with me in the calculator, you need to pause your video right now and type these in a list. And I'm going to call my list data. So if you want to do that, pause now and do it. If you want to just watch, that's fine too. All right. So as you can see here, I typed in my data. The first thing that I always do is go look at a dot plot just to see if I've maybe typed something in wrong. You know, if I typed in 1,000, that would show up here or something like that. So I look at this, and does that look approximately normal? Yeah, ish. I mean, the one thing that doesn't look quite right is this 126, but one data point can't stop you from being approximately normal. So I don't see any obvious skewness. It appears to be symmetrical. And so right now, I don't have any evidence against it being approximately normal. Let's see if I can get any better evidence for it being normal. So I'm going to go back and look over here. As you can see, I've already pulled the one variable statistics. I do want to remind you how to do that though, in case you forgot. So you can just click anywhere over here, go to menu, go to statistics, go to stat calculations, and one variable statistics. We do have one list. And the thing you need to change is your X1 list needs to be the list you put in, whatever you named it. So I already have that calculation on here, so I'm going to hit cancel, but if you hit OK, you should get the same stuff that I have here. All right, and so here's what I'm looking for over here. I want to know what the mean and standard deviation are. So I'm just going to record those real quick here. So for me, I'm taking a picture of my screen so I have them, and I'm going to switch back to my projector screen here. And so what we saw from that is that the mean, x bar, the mean is 114.9. Just for ease, and it's like 0.98, I'm gonna call that 115. And the standard deviation that was recorded was 14.8. And so I'm gonna use the empirical rule to help assess the normality of this data set. And remember the empirical rule. 68% of data fall within one standard deviation of the mean. All right, well, what does that look like for us right now? So we're actually going to use this mean and standard deviation that we have right here, and we're going to figure it out. So as I write this, if I do, the way I'm going to write that is 115 plus or minus 14.8. And what that gives me is the interval from, I'm going to type it in here real quick, the interval from 100.2 all the way up to 129.8. And so what we are expecting is that about 68% of our data fall in that range. So now I'm going to go back and I'm going to look at this data set, and we're going to find out if that's true for this data set. So where is that in here? So 100, where do we breach over 100.2? That's right here. Okay. And then I also have 129.8. So 120 right here. So then the question is, how many data values fall within and how many data values fall outside of that? It looks to me like more of the data values fall outside of that range, so that's what I'm going to count. The way I'm going to do it right now is I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All right, and I'm going to record that over here. So 19 values outside this range, which means that the rest, and there were 60, so that's 41 inside the range, and that's 41 out of the total of 60, and 41 divided by 60 is 68.3%. Holy moly. So y'all, that's as good as it gets, okay? We were expecting that about 68% of the data would fall in that range, and we got 68.3. So right now, what we would say is that is evidence in favor of it being approximately normally distributed. However, we're not done yet. We need to finish the empirical rule. The next part says that 95% of the data fall within 2 standard deviations of the mean. So this is going to start to feel maybe a little bit repetitive, but we're going to repeat this calculation now, except we're going to find the interval for 2 standard deviations away. So that's plus or minus 2 times 14.8, and we're going to get an interval, excuse me. And I get on the low end 85.4. And on the high end, 144.6. All right, let's rinse and repeat. So now I'm going to go back to the data set. And a minute ago, I crossed off a lot of stuff. I'm going to erase all that because now that's covering up data that I need to see. And so we're going to go back again. 85.4, where is the cutoff? That's in between these two. And 144.6, 144.6 would be right in here. And so right away I can see there are 1, 2, 3 values outside. So I'm going to make a note. 3 outside, which means the other 57 inside. and that would be 57 out of 60 of the values that fall inside. And calculator time, that is, oh man, that is exactly 95%. So that matches exactly what we wanted. All right. And then the last part of the empirical rule, we need to test that as well, is that 99.7% fall within 3 standard deviations of the mean. The calculation is going to look quite similar. And so 115 plus or minus 3 standard deviations of 14.8. Calculator time again. And I guess I did the upper one first this time. So I got, for the upper, 159.4. And for the lower, 70.6. So back to the data we go. And at a quick glance, I can see right away that all of the data values fall between 159, 70 and 159. And so without even doing a calculation, it's easy for me to see that 100% of the data are within right here. And so what we have here, we basically, it looks like we probably got spoon-fed a data set here where we got 68% to 68%, 95 to 95, and 100 to 99.7. Now here's the weird thing about statistics is it is a little bit more squishy, so to speak, than mathematics is. With mathematics, we have hard definitions, and you either meet the criteria or you don't. And it's cut and dry, and it doesn't really matter what the opinion is. In statistics, it's way more open-ended. So when we say approximately normal, we're making a judgment call about it and going with it, basically. And that's why sometimes it can be used to lie. Like if you claim that something's approximately normal, but most reasonable people wouldn't think it is, then you can come up with some false conclusions. And so that's something we have to be aware of. In this case, we would say, yeah, this is definitely approximately normal, for sure. This is honestly, guys, as close as it gets. Even if all of these were a few percentage points off, that would still be good enough as long as we don't see any skewness in the dot plot. And we don't. So yeah, this one is definitely. Now, these examples take quite a while. So I hope that you can imagine that like in an alternate universe, if we had different numbers here, and I'll put them in red so you know I'm doing an alternate example. If like instead of 68, we had like 54 and maybe it was like 70 right here and 88, then we don't really have a case that it's approximately normal. So maybe we should make a quick checklist of all the things that we need to look at for assessing normality. So we need to look at the dot plot for skewness. We need to evaluate using the empirical rule. And the final thing we need to do is look at a normal probability plot. Let's get this out of the way. We need to look at a normal probability plot. And so let's learn about that now. Okay, a normal probability plot, what it does, it basically takes your data points and it puts them on a scatter plot where the X value is the actual data point itself, and it correlates that to a Y value that would correspond to a predicted Z score if the data were normally distributed. Okay, so these are not the end all be all, but they are a graph type that we need to know about. Guys, if that part up there doesn't make exact sense, don't sweat it yet, okay? So here's a graph, and here are the data, the dot plot on the left, and as I zoom out, you can see the normal probability plot on the right. And what we're looking for is if the data are approximately normal, then the normal or the probability plot, I should probably label that so you know which one is which. So on the left, this is the dot plot. This is the normal probability plot. Okay, so when the dot plot is approximately normal, the normal probability plot is approximately linear. So let's look at some more examples. So here's another example of a data set and its probability plot on the right. as you can see on the left, or at least I hope you can see, this is a right skewed distribution, so clearly not normal. And you see how we have kind of two things going on in the normal probability plot. We have kind of this logarithmic looking curve going on, and we have big bunches of data all bunched up. So that doesn't look too good. And so it's bunched up there and then more dispersed later. Here's another example. This one, at first glance on the left, you might think that looks approximately normal. But the issue on this one is this one actually does not pass the empirical rule test, and we're not going to run the numbers on it, but what I hope you can see is that the data are really bunched in the middle, and then you have quite a few of these like outlier-y things that make the standard deviation big. And so what we see there is we kind of get two things going on. You kind of have a little bit of curvature, which is not the end of the world, but we have a lot of bunching in the middle, and then we have way less on the outsides. Now I want to go back to the first example to contrast that. See, this one is roughly normal, and you see how there aren't like total clusters of dots along the middle of this thing? So it's roughly linear, and there's, a small amount of curvature in there, but not enough to be interesting. And yeah, there's a point or two on the ends that are kind of lonely, but there's not major bunches in the middle. They're kind of evenly spaced in the middle. That's what we want to see for approximate normality. But don't be too harsh, okay? These don't have to be perfect. For example, every one of these is good enough to say approximately normal. So even though there's a little bit of bunching in here, even though there's a little bit of curvature to this, that's okay. Even though the last one has a little bit of clustering is okay. And again, this is where stats, especially for people who love math, can sometimes be frustrating. Because you're like, wait, I thought you said clustering wasn't okay. Well, a little bit of clustering is okay. Too much clustering is not okay. Well, yeah, but Mr. Boyden, how much is too much clustering? Well, too much is too much, right? That's not very satisfying, is it? So back up here, though, this has got like cluster, cluster, cluster. That's kind of marginal. You're kind of looking at not normal. Here, major clustering and a clear curve. Clearly not anywhere near linear. Okay, those are definitely not approximately normal data sets. So let's go look at what the normal probability plot would look like for the one we just did. In fact, I'll go ahead and pull it up now. To do so, you can just pull up your dot plot again if you want, hit the menu button, and on plot type, you'll notice there's a normal probability plot option. And there it is. Now our calculator is nice enough to give us an equation. We're probably never going to use that, but thanks, calculator. That's super nice of you. What I hope you see here is on the very far left, there are a couple of sort of lone points, and on the right, there's a lone point or two, and in the middle, it's pretty darn linear, and there's not any extreme clusters. There's a little bit of a gap here, but that's not enough to cause us to question whether or not our data are approximately normal. That's going to be all for today. Hope you enjoyed it, and I'll see you next time.